I'll start with today's class. I hope the screen is visible. Welcome to the week 3 of Transport Phenomena course. Uh, this course is guided under Professor Sunando Dasgupta of IIT Kharagpur. He's an instructor and guide of mine. So I am the TA of this course, and I would be today proceeding with the week 3 of the problem solving class of transport phenomena. Okay, so without further ado, I'll go to the question number 1. So this is the question number 1, is it is displayed on the screen. Two plates separated by a distance b form a channel. Okay, so one of the plate is porous and the other plate is permeable. Okay, so a flow is taking place in between those channels, so that the x component of velocity u is a function of x only, and its value at the inlet is u naught. This is uniform flow v naught through the porous wall. There is a uniform flow u naught through the porous wall to the V naught through the porous wall, that is the downward plate, to the channel, so that the velocity v is the component of y direction only within the channel and is function of y only. Okay, so considering the flow to be incompressible, find the expression of u as a function of x. Okay, so how should we proceed with this question? Here it is clearly indicated that u, that is the x direction of velocity, the x component velocity, that is u, is a function of x only, and y component of velocity, that is v, is a function of y only. So we have to find the velocity profile. So how we can proceed is that, and it is said that the flow is incompressible. So we can simply start with the continuity equation. So if we start with the continuity equation, gradually solving the continuity equation, and then coming to the, from the continuity equation, we can get a we can start with the solution. So you proceed with the solution. I'll give you 5 minutes for solving this, and after that we'll go with the solution. Okay. Okay. So it's time I should start with the solution. I'll share with my writing pad screen. Check whether it's visible or not. I hope the writing pad is visible. Okay. So first this is question number 1. Equation of continuity at any point within the channel can be written as del u del x plus del v del y is equal to 0. Okay. This is the continuity equation. From here we get del u del x is equal to minus del v del y. Let's suppose this is equation number 1. Okay. Now, since u is function of x only and v is a function of y only, the equality of the derivatives are expressed in equation 1 would be valid provided if both of them are equal to a constant. Like this will be valid if both of them are equal to a constant. So we can write them equal to a constant. So del u, we can write this like this. Du dx is equal to minus dv dy is equal to k. That is a constant, right? This gives du dx is equal to k, that is 1, and dv dy is equal to minus k, that is 3. Okay, so integrating equation 1 and 3, we get small u is equal to kx plus c1 and v is equal to minus ky plus c2. This is for this equation 5. Okay. Mm, now, uh, now what are the boundary conditions? The boundary conditions are at x is equal to 0, u is equal to u naught, and at y is equal to 0, v is equal to v naught, and at y is equal to b, b is equal to 0. Okay, as we can clearly see from the question. In equation 4 and 5, we have u naught is equal to c1, v naught is equal to c2, 0 is equal to minus kv plus v naught, or from this we can get k is equal to v naught by b. Therefore, in equation 4 and 5, substituting values of k, c1 and c2, the final expression for U is obtained as U is equal to V naught by V x plus U naught. So with what option it is equal to? As we can see from the question, it is equal to option A. Okay. So this will be the solution of question number 1. Now let us proceed to question number 2. So for the question number 2, let us take an overview of the Navier-Stokes equation. It will be required. So for the overview of Navier-Stokes equation, we know that the continuity equation is del dot V is equal to 0 and the momentum equation is rho substantial derivative of v del v del t dv dt, that is the total derivative, substantial derivative that can be obviously like diverse to rho del v del t, that is change of velocity with respect to time, and v dot del v, that is the convective term of the velocity, and that will be is equal to the pressure gradient, that is minus del p, plus rho g, that is the body force term, and plus mu v del square v, that is the diffusion term. This is the viscous term, and the gravitational force term, body force term, that is here gravitational force, and the pressure gradient term. Okay. Uh, uh, Now let us proceed to question number 2. So in a fully developed flow, what happens? The pressure gradient is greater than the wall shear stress, or the pressure gradient balances the wall shear stress only and has a constant value, or the inertia force balances the wall shear stress, or none of that. What will be the question? Like what will be the line or the sentence that will be related to the fully developed flow? Let us select one option. So I'll give you 10 minutes or actually 5 minutes to answer this question, and after that we'll go for the solution. I'll proceed with some basic things that is related to this problem, and then we will understand clearly, like with some basic derivations, that which of these options will be true. Okay. Okay. So okay. So we'll go for the solution of question number 2. I'll show some basic derivation to understand and to get on to the point where like which one will be the perfect solution for like perfect statement for the question number 2. That is the for the full irregular flow. Okay. Okay. So let's start. So question number 2. Navier-Stokes equation is minus del P plus rho G bar plus mu del square V bar is equal to rho dV bar dt. Okay. So now the assumptions for laminar. Now we'll do some basic derivation for laminar flow through a circular pipe. Okay. So assumptions are for this will be first is steady state flow, then is uniform flow, then is one dimensional flow, then fully developed flow, that is u is a function of r and u is not a function of x, where there is a pipe, this is the center, this is r, and this is an element. Dx. Okay. So in this direction, PdA is equal to P pi r square. This is the input pressure, and this is at r is equal to 0. Okay, and this is the output pressure. This is pressure force dp x. This is the change in pressure when it is traveling through that fluid element. Let me del x cos this is del x dx into pi r square. Okay. Now from Newton's second law of motion, summation of all forces is equal to mass into acceleration. If acceleration is equal to 0, as in a fully developed flow, no acceleration is there. Okay. So summation of forces is equal to 0. When horizontal weight force is negligible. Okay. Okay. As the pipe is horizontal, the weight force is negligible. That is, the gravity is not considered. Two forces applied. One is pressure force and two is shear force, that is Fs is equal to tau s dA is equal to tau s into 2 pi r dA. Now, balancing the forces. Input pressure force minus output pressure force is equal to shear force. P into pi r square minus P plus del P del X okay. Del P del X dx pi r square is equal to shear stress into 2 pi r dx is equal to, because the rest of the things is not there. So minus del P del X dx pi r square is equal to tau s 2 pi r dx. Okay. So this gives tau s is equal to minus r by 2 del P del X. If the flow was uniform, then del P del X is equal to constant. This shows the shear stress distribution is linear. That is, at r is equal to 0, tau s is equal to 0. No shear stress. At wall, tau s is max, same. That is tau s max or tau w is equal to minus r by 2 dp dx. Okay. So, if we'll find the velocity profile, this will be like that. This is the center, sorry, the shear stress profile. This will be the shear stress profile. Okay. This is r is equal to 0. This is tau w is equal to minus r by 2 dp dx. Okay. Now, if we not consider uniform flow, then dp dx may or may not be constant. Thus, the generalized equation is 2 tau w by r is equal to del p del x. So, from this equation, it indicates that the pressure gradient in the direction of the flow is equal to the shear stress gradient in the direction normal to the flow. So, and this equation holds for all types of geometries. Okay, so this help us to determine like in fully developed flow which of these statements we can apply. So it is clear that statement B, that is the pressure gradient balances the wall shear stress and has a constant value, is applied. Okay. Okay. So let us proceed to the question number 3. Consider all the statement, even if one of them is wrong, then mark the entire answer as false, else mark it as true. If one intends to obtain a velocity profile for the flow around a aeroplane wings, that is airplane means aeroplane wings, except near the solid boundary, the viscous forces is assumed to be relatively unimportant and the Euler equation for inviscid fluid is deemed to be suitable for solving the velocity distribution. Answer whether it is true or it is false. I'll give you 5 minutes for this and then we'll come up with the solution. I hope you understood the previous solution. If anyone have any doubt, kindly unmute yourself and ping me for the same. Okay. If no one has any doubt, then we'll wait for question number 3. So, question number 3, you kindly proceed for the solution. Okay, so as I have not received any answer, I'll go on with the. Okay, so I have not received any answer yet, so I think I'll go with the solution now. I hope the writing pad is visible. Okay, writing pad is visible, and the question is also visible to you. So it will be question number 3, right? Here, the viscous forces are assumed to be relatively unimportant. If viscous force is relatively unimportant, then the flow is invisible. And here the fluid is air. Okay, so if the fluid is air and the flow is and the viscous forces are also unimportant, the flow can be considered as invisible. Fluid is air and viscous forces are unimportant. This makes flow is invisible. Okay, again, as air is there, so density is also constant. That means flow is incompressible. So what we know now? Flow is incompressible and invisible. This makes flow is ideal. Thus, for ideal flow, Euler's equation is valid. So, Euler's equation can be applied. Okay. So, this makes what? Answer is true. That is option A. Now, we'll go with question number 4. Okay. Okay. Let us proceed to question number 4. So, the question number 4, okay. A continuous belt is there that is passing upward in a chemical bath at a velocity of u naught. So what is happening? There is a bath. There is a bath of chemical fluid. So what is happening is that it is picking up the liquid with it of thickness and a film is thin. Film is forming of height of thickness h, density rho, and viscosity mu. Gravity tends to drain the liquid, but because of the movement of the belt, liquid, the liquid uh, keeps the liquid from running down completely. Because of the movement of the belt, the fluid doesn't run down. It is moving up with a thin film, like a thin film. Assume that the flow is fully developed and the atmosphere produces no shear at the outer surface. So the shear stress will be 0. And what we need to do, we need to, first question is that there is link question, and the question will be there. First question is, what is the boundary condition that is required for the velocity function? Okay. So what will be the boundary condition? Uh, okay. Let us see. At this is y. At y is equal to 0, u is equal to u naught. What is one thing? At y is equal to 0, u is equal to u naught is 1. At y is equal to h, shear stress is 0. That is du dy is equal to 0. That is answer is option number B. Okay, it's understood, right? And then we'll go for question number 5. What is question number 5? Choose the correct option for the equation of the velocity profile for the system depicted in question number 4. So we need to find the velocity profile. So this you give it a try, and after that I'll go for the solution. Okay, so we'll wait for 5 minutes for you to give it a try. Okay. Now we'll choose first okay. This is the diagram, right? Let us start with the diagram itself. Okay. So by choosing a control, we'll choose a control volume first of size of arbitrary length and width L and W and a thickness delta Y and performing momentum balance, one can obtain the governing equation as follows. Okay. So this is the plate. This is the plate. This is the fluid film. Okay. So we have taken one patch of a patch of elemental volume. So its length is L, width in this direction is W, and its thickness is delta Y. Okay. So now the momentum balance is convective. First is convection, will check convective mass in is equal to convective mass out. That is, no convective momentum contribution is there. No convective momentum contribution is there. And again, flow is fully developed. So, no pressure gradient is there. As flow is fully developed, no pressure gradient is there. Pressure gradient won't be there. Therefore, if we do the balance, tau yx at y, Lw minus tau yx at y plus del y Lw minus Lw del y rho g. This is the gravity force. This is negative as the flow is happening just opposite to the direction of gravity. Okay. Now, dividing by del y Lw on both sides, that is minus tau yx y plus del y minus tau yx at y by del y minus rho g is equal to 0. Taking limit del y tends to 0, we get limit del y tends to 0, tau yx at y plus del y minus tau yx at y upon del y minus rho g is equal to 0. Okay. So what this makes d dy of tau yx minus rho g is equal to 0, or minus d dy minus mu du dy minus rho g is equal to 0, or mu d square u dy square is equal to rho g, or mu du dy is equal to rho gy plus c1. if we integrate. So du dy is equal to rho gy by mu plus c1 by mu, or u is equal to rho gy squared by 2 mu plus c1 by mu y plus c2. Now what are the boundary condition? At y is equal to 0, u is equal to u naught. So u naught is equal to c2 and u is equal to rho gy square by 2 mu plus c1 by mu y plus u naught. Okay. So at y is equal to h, tau is equal to 0. So du dy is equal to 0. This is the boundary condition 2. This was 1. This will give du dy is equal to rho g2h by 2 mu plus c1 by mu is equal to 0. Or this gives 2 kata. So this gives c1 is equal to minus rho gh. Okay. Therefore, u is equal to rho gy square by 2 mu minus rho gh mu y plus u naught. So u is equal to rho g by mu y square by 2 minus hy plus u naught. This is the corresponding velocity profile. So let us check the question number 5. Which option is correct for us? So this is option number A. Answer is option number A. Okay. Okay. Now question number 6. Let us proceed to question number 6. Consider all the statement, and even if one of them is wrong, then mark the entire answer as false, else mark it as true. The Navier-Stokes equation are not amenable to an analytical solution due to the non-linear inertial terms present in it. Okay. However, in Poisson's flow, the non-linear initial terms are reduced to 0 and the exact solution of Navier-Stokes is obtainable. Okay, check out this question for 3 to 4 minutes and we'll get back to the solution after that. Okay. So let us now proceed with the solution. I hope I am audible and visible. Okay. So let us proceed with the solution now of question number 6. So for question number 6, we'll again write the Navier-Stokes equation. This is rho dv bar dt is equal to rho g minus del p plus mu del square v bar. Now the inertial term, which one is the inertial term? Inertial term is dv bar dt. That is equal to del v bar del t plus del v bar del x vx plus del v bar del y vy plus del v bar del z vz. So this whole term makes the Navier-Stokes equation non-linear. Okay. So, what is the Poiseuille's flow? Poiseuille's flow is basically the pressure-induced flow in a long duct, usually in a pipe. It is distinguished from the drag-induced flow, such as Cauchy flow. Especially, it is assumed that there is laminar flow of an incompressible Newtonian fluid of viscosity eta induced by a constant positive pressure difference or pressure drop del P in a pipe of length L and radius R is far less as compared to L. By a pipe, it is meant that right angle circular cylindrical duct, that is a duct with cross section normal to its axis. So, what is Poiseuille's flow? Poiseuille's flow is fully developed flow. That is, U is independent of axial position, Z is Z, and everywhere except an entrance and the exit of the pipe. Poiseuille's flow is irrotational and also axisymmetric. So, Poiseuille's flow is basically the pressure-induced flow. Second is its fully developed flow. Third is its irrotational, and fourth is axisymmetric. Thus, the nonlinear term in the Poiseuille's flow is reduced to zero, as everything is cutting out here. Like everything in this inertial term is reduced to zero. Thus, the Poiseuille's flow is in Poiseuille's flow. This the nonlinear inertial term is reduced to zero. Thus, you can directly find the exact solution of the Navier-Stokes equation if Poiseuille's flow is considered. So yes, this solution is what? This solution is true. That is 6 number answer is A. Now let us proceed to question number 7. Okay. So what is the question number 7? Water at 60 degrees Celsius flows between two large flagellates. The lower plate moves to the left at a velocity of 0.3 meters per second, and the plate spacing is 3 mm and the flow is laminar. Determine the pressure gradient required to produce zero net flow at a cross section. That is, flow rate will be zero. Flow rate per unit width at any cross section as it is determined. So we will find flow rate per unit like pressure gradient per unit width as in the units we can see from the solution it is per unit width. Okay. So I'll give you 5 minutes to solve this, and after that we'll go with the solution. Okay. Okay, so now we'll start with the solution of this question, that is question number 7. Okay. mm, Now we will choose first a control volume of size of arbitrary length and width L and W and of thickness delta Y and performing momentum balance, we can obtain the governing equation in presence of imposed pressure gradient. But no body force in the direction of flow. No gravity as flow is horizontal. Okay. So let us now do the momentum balance. Tau yx, as this is x momentum that is transferred in y direction. Okay. Tau yx at y, Lw minus tau yx at y plus del y, Lw minus P naught. There is pressure in this direction. So this will be W del y plus PL, that is the pressure out, at W del y is equal to 0. So now dividing by L del y W, we get minus tau yx at y plus del y minus tau yx at y upon del y minus P naught minus PL by L is equal to 0. Now if we take limit here, then this will get reduced to dy of tau yx is equal to dp dx. Dp dx, as this is changed to dp dx, as dp dx is the pressure that varies along pressure varies along x direction. That's why this can be written as dp dx. Now tau yx is equal to minus mu du dy. As y increases, velocity decreases. That's why this minus term comes. This minus comes. Okay. So therefore this equation gets changed to du dy minus mu du dy is equal to dp dx, or d square u dy square is equal to 1 by mu dp dx, or du now integrating 1 by mu dp dx into y plus c1. Again d again u again this u is equal to dp dx y square by 2 mu plus c1 y plus c2. This is the main equation. Now we will put the boundary conditions. The boundary condition, the first boundary condition is that y is equal to 0, u is equal to minus u. And second one is at y is equal to b, u is equal to 0. Now putting boundary condition 1, minus u is equal to c2, u is equal to dp dx y square by 2 mu plus c1 y minus u. dp dx y square by 2 mu c1 y minus u. Okay. So now putting boundary condition 2, that is which one? This one. 0 is equal to dp dx into b square by 2 mu plus c1b minus u, or c1 is equal to u by b minus dp dx b square by 2 mu into 1 by b. So therefore c1 becomes u by b minus b by 2 mu dp dx. Therefore u is equal to dp dx y square by 2 mu plus u by by minus b by 2 mu dp dx into y minus u. So small u is equal to 1 by 2 mu dp dx y square minus by plus u y by b minus 1. This is the main equation. Now, what is our question? The pressure gradient we need to determine for zero net flow at the cross section. So to find the zero net flow, we need to first find the flow rate upon width. So this is 0 to b u dy into 1. Width we have taken as unity. So this is 0 to b 1 by 2 mu dp dx y square minus by plus u y by b minus 1 dy is equal to 1 by 2 mu dp dx y cube by 3 minus by square by 2 0 to b plus u y square by 2b minus y 0 to b. Okay, so 1 by 2 mu dp dx b cube by 3 minus b square by 2 b cube by 2 plus u b square by 2b minus b. So what q becomes? This becomes 1 by 2 mu dp dx minus b cube by 6 plus u minus b by 2. Therefore, q by w becomes minus 1 by mu dp dx b cube by 2l plus minus bu by 2. Now we need to make it 0. So if we make it 0, it will be minus 1 by mu dp dx b cube by 12 minus bu by 12, not 12, this will be 2 is equal to 0.
or dp dx is equal to minus u by 2 into 12 mu by b square 6 is equal to minus 6 u mu by b square. So this is minus 6 into u is 0.3 meter per second into 4.7 into 10 to the power minus 4 Newton second per meter square by 0.003 square meter square. Okay, so this becomes minus 94 Newton per meter square into meter dp dx. Answer, what will be the answer? This is B. Yes. So this is the answer for question number 7. Now let us proceed to question number 8. Okay, consider all the statement is true. Even if one of them is false, then mark the entire answer as false. Okay, in Couette flow, for a negative pressure gradient in the direction of motion, the velocity is positive through the whole gap between the channel walls. For a negative value of pressure, there is a positive pressure gradient in the direction of motion, and the velocity over a portion of channel width can be negative and backflow may occur near the wall, which is at rest. Okay, so let us take 2 minutes in here so that you can answer the question. Okay, so we'll now go proceed on with the solution of this. So Quade flow we have already studied in our classes. Like sir have already taught you this. So as far as you remember the graph of the profile velocity profiles for the Quade flow for different pressure gradient, it will be like this. This, this, and this. This is for dp dx negative. This is for dp dx is 0, no pressure gradient. And this is for dp dx is equal to positive. That is, as we can see here, backflow is there. This one is backflow. This is y by b is equal to 0. This is y by b is equal to 1. This is backflow. This plate is moving at a velocity u. This is favorable pressure gradient, this is unfavorable pressure gradient, but this is backflow. So as it is indicated in the question that the negative pressure gradient direction of the motion, the velocity is positive through the whole gap. The velocity is positive through the whole gap between the channel walls for a negative value of p, and there is a positive pressure gradient in the direction of motion, and the velocity over a portion of the channel width can become negative, and backflow may occur near the wall, which is at rest. So obviously it is true. So answer will be A. That is true. Now we'll proceed on with question number 9. Okay. Uh, what is this question? In many situations, the velocity depends on both position and time, and the flow is described to be partial differential equation. The solution of the partial differential equation can be the method of combination of variables, where the initial condition and the boundary condition at infinite, that is infinity, may be combined into a single new boundary condition. The method of separation of variables, where the partial differential equation is split up into two or more ordinary differential equations. This is true. This is true. Yeah. So this is rather simple problem. So this is true. That is solution will be B. B is true. Now we'll go for question number 10. Okay. So a semi-infinite body of liquid with a constant density and viscosity is bounded by a horizontal surface. Initially the fluid and the solid are at rest. Then at time t is equal to 0, the solid surface is set in motion in the positive x direction with velocity v0. Choose the option with the correct initial boundary condition, assuming there is no pressure gradient or gravity force in the x direction and the laminar flow. Okay. So it is said that at t0 fluid is at rest, and when t is greater than 0, that is after time t is equal to 0, the ball is set in motion, and there will be unsteady flow. So what will be the initial and the final boundary conditions? Initial boundary conditions and the initial boundary conditions and the other boundary conditions. And the other boundary conditions. Okay, so I'll give you 2 minutes to solve this, and after that we'll go on with the solution. This is rather simple question, so just you have to identify the boundary conditions. So I'll give you 2 minutes for this because we have two more questions. I don't think whether whether or not I'll be able to solve the last question, but yes, one more question we'll solve today. Okay. uh, we can will now proceed with question number 10. Like this simple boundary condition that we need to solve. Like what the boundary condition we need to determine that. Okay. So it is said that initially the fluid and solid are at rest. So initial condition is at t less than is equal to 0, Vx is equal to 0 for all y. Okay. So this determines that at t is equal to 0 and okay. So this is initial condition. Now at t is equal to 0, solid surface is set in motion in positive x with v naught velocity. Okay. So boundary condition 1 will be initial condition, boundary condition. So boundary condition 1 will be at y is equal to 0, Vx is equal to v naught. Vx is equal to v naught, yeah, for all t greater than 0. And boundary condition 2 is at y is equal to infinite. At infinite, there will be no effect of the solid wall, movement of the solid wall. That's why there will be negligible disturbance. So Vx will be at infinite. The fluid will be at rest. That is, there will be no velocity of the fluid. Okay. So Vx is 0. Vx is 0 for all t greater than 0. So what will be the answer? Answer is A. Okay. Now we'll go with problem number 11. So let us proceed to the problem number 11. Okay. So the velocity distribution in laminar boundary layer over a flat plate is assumed to be U is equal to A sine by plus C, where A, B and C are constant. So apply the proper boundary condition and determine the velocity distribution law. So this is rather same question that we have earlier done. We just have to determine A, B and C and determine the velocity profile for the same. And before that we need to determine the boundary conditions. Okay, so I'll give you 5 minutes to solve this as we have 15 minutes more left. So I'll give you 5 minutes to solve this and after that we'll undergo with the solution. Okay.
Okay, it's time, so we'll start with the solution now. Okay, there are 10 more minutes left, 9 more minutes left. So, we'll proceed with the solution of this question number 11. Okay, so first let us draw the flat plate. So it is said that flat plate, so this is the flat plate boundary layer. At y is equal to 0, u is equal to 0 obviously, and at y is equal to delta. This is delta, right? Boundary layer thickness. And u is equal to u naught. And also shear stress is also 0 at this point, at this boundary. So du dy is equal to 0. This is the flow, this is the potential flow, that is free stream velocity u naught. So at wall surface y is equal to 0 and u is equal to 0, a sine b into 0 plus c, or c is equal to 0. Okay, then then u is equal to a sine by, right? U is equal to what? U is equal to a sine by, as we can see from the question, as c is 0. So now at the outer edge of boundary layer, that is y is equal to delta. This we have already pointed out here, at y is equal to delta, what will be the boundary conditions. So at this, u is equal to u naught, free stream velocity, and shear stress is 0, so du dy is equal to 0. If we put this in this equation, these two, we will get two equations, right? One is u naught is equal to a sine b delta. This is equation number 1. And another is du dy is equal to, at y is equal to delta, is equal to ab cos b delta. And b delta is equal to 0. This is equation number 2. Now here, from here we can get a. So we will put value of a from 1 in equation 2. By doing this, we get u naught by sine b delta b cos b delta is equal to 0, or u naught b cot b delta is equal to 0. This is the equation. Now b cannot be 0, as b cannot be 0, as that will make the velocity 0. Velocity 0 at any cross section throughout the boundary layer region. That is not possible. Okay. So what will happen then? This thing is not 0, this thing is not 0, so this will be 0 obviously. So cot b delta is equal to 0. Now what value of cot gives 0? Cot pi by 2 is equal to 0. Therefore b delta is equal to pi by 2, or b is equal to pi by 2 delta. Okay. Then from equation 1,
Which is equation 1? Equation 1 is this one. U naught is equal to A sine B delta. Right. So U naught is equal to A sine B value, we'll just put, the value of B will just put 2 delta. Uh, into delta. Okay. Delta delta will be cut off. So A sine pi by 2. Sine pi by 2 is 1. So A is equal to U naught. A value we have got. So substituting these values of constants A and B in expression of U, we get U is equal to A sine by. That is U is equal to U naught sine pi by 2 delta into y. So this is the answer. Okay, we are left with one more question, but today there is no time and this is a fairly big question. So we will proceed, like we will take up this question on the next week. Okay, so I'll stop sharing. Okay. Thank you for being here, and I'll meet you all next week. Thank you.